Hi there, I'm Jianming Tong, PhD student at Georgia Institute of Technology. I'm so thrilled to introducing our collaborative work with IBM, which is published at ISCA 2024. It is called FEATHER, a reconfigurable accelerator with data reordering support for low-cost on-chip data flow switching. Let's start with some background to set up the context. The size of machine learning model increases exponentially over the year, coming with billions of parameters. This introduces both computation challenge and also energy challenge because of heavy data movement across memory hierarchy. Both challenges motivate people to build dedicated accelerator for better energy efficiency over existing designs. Example including EIE, Average, Simba, etc. In the high level, all accelerators could be abstracted as special 2D computation array with custom memory hierarchy. This tackles computation challenge by spreading compute across seeds of ALUs and removes heavy data movement by reusing data via local storage or direct communication. To achieve maximum data reuse, the key is to explore data flow. We define data flow as fine-grained compute and memory scheduling over space and time. As for convolution, data flow could be represented as two levels of nested loops. The order of dimension refers data reuse over time, and the parallelism of dimensions defines data reuse over space. When giving each dimension with a specific telling value, the nested loop becomes an actual mapping. We use mapping and data flow interchangeably in the rest of the talk. However, the design space for data flow is extremely large. Even a single convolution layer comes with 10 to the 26 different data flow choices. Different choices give different performance as shown by the black arrow bar. And there is no global optimal data flow for all different types of layers. Adaptive switching among optimal data flows for each layer will give us 2x theoretical speedup. Therefore, lots of accelerators focus on enabling flexible data flow, such as Sigma and Flexicon. But all of them ignore data layout in the on-chip buffer. We define data layout as fine-grained organization of data in the on-chip buffer. Specifically, how to determine the row and column positions of data in the on-chip buffer. We term the order of row position and the order of column positions as interline dimensional order and intraline dimensional order separately. Both dimensional order could be represented as nested loops. Taking interline nested loop as an example, the first iteration specifies 16 data from C dimensions, shown by the right elements on the left. These 16 data will be stored in the first line of on-chip buffer. Similarly, evaluating the second iteration specify another 16 data from C dimension and store them into the second line of your on-chip buffer. Evaluating all iterations will specify the layout of data across different lines. Further, evaluating intraline nested loop specifies the dimensional order within a single line, such as here. Therefore, a given layout is named as interline dimension order underscore intraline dimensional order. For example, the layout above is named as HWC underscore WX1 HX1 CX16, where X indicates parallelism. It could be further get simplified into HWC underscore CX16 to skip the dimension without parallelism. When considering the realistic data layout, the performance of green bar will become yellow bar. Among these, we see up to 128x theory practice performance degradation because of bank conflict. Let's take an example to illustrate why bank conflict is so severe. For a layer with 32 input channels and 32 kernels, where both C and M equal to 32, a 2D array leverage CM data parallel will read 16 data from C dimension per cycle, as shown by these green transparent boxes. To satisfy such demand of data flow, the ideal layout is to arrange all these 16 data into one row of on-chip buffer. Under this layout, the data flow will raise a single row every single cycle to fit into the computation array. This gives the following reading traces and 100% utilization of computation array. This is because data flow and layout matches each other. And we call this as concordant data flow layout pair. In other words, concordant layout achieves the theoretical computation utilization of a given data flow. However, when workload changes into a layer with only 8 input channels, but a large number of head and width, this previous CM parallel data flow will only give us 50% overall utilization. Therefore, we will switch data flow into WM parallelism to read 16 data from W dimension instead, as shown by these green transparent boxes. If data layout doesn't get changed, these 16 data from W dimension will locate it at 8 separate lines, as shown here. Reading 8 rows from a buffer with 2 ports takes 4 cycles, leading to bank conflict slowdown. In short, even though this data flow has 100% utilization theoretically, it suffers from 4x bank conflict slowdown in practice and only delivers 25% utilization in practice. This is because data flow and layout doesn't match each other, and we call such a mismatching as discordance. To solve this work proposed layout reordering to change the previous layout into a new layout where we're stacking 16 data from W dimension into a single row of the on-chip buffer, such that only a single row is required per cycle. This resolves bank conflict slowdown. In summary, to resolve bank conflicts requires data flow layout code switching. Therefore, Feather proposed new architecture to enable on-chip data flow layout code switching to achieve optimal performance, as shown by the red bar. With this overall motivation, let's now formalize the problem, including bank conflict and also layout transformation. Bank conflicts occur when data flow and layout do not match each other. We define this mismatch as discordance. A data flow layout pair is discordant when 2 nested loops with each other are not isomorphic. This leads to bank conflict slowdown. The reason of bank conflict slowdown is shown below. In on-chip SRAMs, a single bank only provides dual ports for reading or writing up to 2 lines per cycle. This access limit restricts the total amount of data that can be read from an on-chip SRAM per bank per cycle. Consider this HWC CX16 layout. It can provide up to 32 data from C dimension, or 2 data from W dimension, or 2 data from H dimension per cycle. If a data flow requires more data than this capacity, multiple cycles are required to provide this data. We term this multiple cycle latency as bank conflict slowdown. To resolve this, the key is to reorder the data layout to make it concordant with data flow. Further, this reordering also enhances spatial locality, leading to better performance. Reordering changes layout to resolve bank conflict. In other words, reordering achieves layout transformation. We formally define layout transformation as changing interline and intraline position of elements in the on-chip buffer. Specifically, to transform a layout is to pick elements from one layout and then store them into new position and the new layout. Let's take an example. Say we want to change layout from channel-less into row major. The detailed data layout in the on-chip buffer is shown below. For every element input activation HWC, the interline position and intraline position could be obtained through the following equations. Both equations are derived from the right-hand side nested loop. When picking the top left element input activation 0, 0, 0. Both interline position and intraline position are 0. So it is also located at the top left position in the new layout. And the second element, IACT001, will be routed to different row. And input activation 010 will be routed to a different column. Input activation 011 will be routed to a completely new location with both new column and new row. Therefore, to achieve arbitrary layout transformation, we need arbitrary row-wise reordering and arbitrary column-wise reordering. With the goal of supporting arbitrary row-wise and column-wise reordering, let's now discussing the challenges of how to implement them in the hardware. Enabling on-chip hardware layout reordering introduces two questions. First, functionality-wise, what kind of hardware reordering is required? Second, performance-wise, how to implement reordering with minimum latency overhead. To understand the functionality demand first, let's take an overview of all available hardware reordering techniques. As I mentioned before, an on-chip SRAM bank provides 2 rows of data per cycle by default. And reordering transforms the layout to provide more data access choice per cycle. For example, layout transpose enables accessing 2 rows or 2 columns of data per cycle. Line rotate moves 1 row from bank 0 into bank 1 to provide accessing of 3 rows per cycle from bank 0. In-row reorder changes the order of data within a single row, and arbitrary reordering enables arbitrary accessing of 8 elements within the entire bank. Existing hardware reordering techniques proposed by prior work, such as Google TPV4 and Meta MPIA, only support a subset of data flow without bank conflict, as shown on the following below. While arbitrary reordering is the only one that ensures 0 bank conflict for all data flow choices. Therefore, Feather picks arbitrary reordering as functionality target. Given this functionality target, different implementations give different latency. Prior solutions like TPV4 and MPIA perform reorder after reduction. In RAR, data reordering is performed after the actual data compute and data reduction. This exposes the reorder latency to the critical path. In this work, Feather integrates the reordering into data reduction to achieve reorder in reduction, RIR. RIR has the reordering latency completely behind the data reduction to avoid reordering latency overhead. To enable arbitrary reordering with negligible latency, Feather proposed a non-chip novel reconfigurable NOC, termed as BIRD. To further enable data flow switching, Feather proposed a reconfigurable 2D computation array called Nest. Both BIRD and Nest make Feather the first accelerator to perform data flow layout code switching per layer. Further, to decide what data flow and layout pair to switch, Feather augments time loop with layout consideration to co-search the optimal data flow layout pair per layer. Let's now unveil how Feather achieves data flow layout code switching in detail. This diagram shows the overview of Feather. Feather performs computation in the loop. Specifically, Feather reads data from green stationary buffer, changes data layout in compute, and writes results back to the stationary buffer with the new data layout. This loop of compute enables Feather to code switch data flow layout per iteration. Within the computation pipeline, Nest supports data flow flexibility, while BIRD enables layout flexibility. Let's first deep dive into the microarchitecture of Nest, and then see how it supports flexible data flow. Nest means neural engine for spatial forwarding and temporal reduction. Neural engine refers to the 2D computation array with array head by array wise P elements. Spatial forwarding means both green input activation and blue weights move from top to the bottom in the pipeline manner. Temporal reduction means each PE has array-head ping-pong local registers to hold weights for temporal reduction. Such local registers enable PE at a column to reuse the same column-wise output bus. Each write output bus sends temporarily reduced partial sum from PE to BERT for column-wise reduction. The post-reduction results will be written back to the stationary buffer in the new layout that is concordant with the next data flow. Let's take an example to see how next works. For mapping a 2x2 convolution down to a 4x4 nest array, from workload side, each kernel has 2 head, 2 west, 2 channel. The convolution operator requires each kernel to slide on the input activation in the razor scan manner shown on the right arrow. From the hardware side, each PE in the 4x4 nest array has 4 ping-pong local registers, such that each PE could hold a single channel of a kernel. In this way, 16 PE holds the first channel of 16 kernels in total. Under such mapping, all PEs reuse the same input activation. Therefore, we load a single input activation per cycle and feed them in the top PE row. For example, in cycle 0, we load the first write element into the top PE row. And each PE in the row multiply the write input activation with the first local weight, W0, to generate a partial sum. The partial sum will be stored locally for temporal reduction with other 3 partial sums within the same sliding window. In cycle 1, the second purple element is loaded to the top PE row, and it will be multiplied with the second local weight, W1, to update the partial sum. Simultaneously, the write input activation will be forwarded to the next row to multiply with the first local weight there. At cycle 2, the third green input activation is loaded to the top PE row to further update the local partial sum. After 4 cycles at cycle 3, the top PE row finishes the temporal reduction of a channel. Therefore, PEs at the top row will activate the column-wise bus to send the results to BERT for column-wise reordering and reduction. The spatial forwarding introducing 1 cycle pipeline latency for every single row. This natural 1 cycle pipeline latency makes the second PE rows finishing reduction exactly 1 cycle after the top row. Therefore, the second PE row will take over the column-wise bus at cycle 4. Similarly, the third PE row take over the column-wise bus 1 cycle after, followed by the last row to take it over at cycle 6. After it, the top PE row completes the temporal reduction of the next sliding window, such that it will take over the column-wise bus back again. In summary, in the steady state, only a single PE per column will activate the column-wise bus per cycle, while other PEs within the same column performing local temporal reduction. This makes all PEs busy and achieves 100% peak computation utilization. Such a microarchitecture enables NAS to support data flow flexibility. The key reasons boils down to 3 levels of data reduction. First, each PE performs temporal local reduction. Second, further leverage BERT to enable arbitrary column-wise spatial reduction. Third, further uses output buffer to enable temporal row-wise reduction. More details in the paper. Given the data flow flexibility, let's now deep dive into the microarchitecture of BERT and introduces how it enables arbitrary layout reordering. BERT is short for butterfly interconnect for reordering in reduction of data flow. BERT's input connected to column-wise output bus of a nest, while BERT's outputs are sent to output buffer, quantization module, and eventually go back to bank of stationary buffer shown in green. Specifically, an input bird has 2 log n pipeline stages. Each stage contains n over 2 2x2 switch. Each switch is called an egg. Each egg supports 4 functionality to perform both data reordering and data reduction together. It could take 2 inputs, swap them, send them out. Or it can directly take input to the output. It could be also configured to add both input and roll the result to left output or the right output. This topology with such functionalities enable BERT to perform arbitrary reduction to accumulate any selected input data, and also arbitrary reordering to reorder the accumulated results to any output port. Therefore, BERT performs both reordering and reduction on the output data of Nest. Such an reordering in reduction, RIR, enables Feather to achieve full layout flexibility. Taking the 4-input BERT as an example, which takes 4 outputs from Nest. The outputs share the same color need to be reduced together. For example, the 4-input BERT performs 2 groups of 2,1 reduction to reduce 2 blue data into 1 and rotate the results into column 0, and also 2 brown data into 1 and roll the results into column 3. Further, BERT could reorder the accumulated results to different banks, as shown by sending accumulated blue data into column 2 and accumulated brown data to column 0. BERT could also be configured to perform pure permutation without reduction, or multiple reduction groups with different sizes, such as a combine of 3,1 reduction and a 1x1, or even a all reduce. Such reordering reduction enables Feather to achieve arbitrary layout transform. Let's take an example. Say that we have a input BERT and want to convert from HWC CX8 into HWC WX8 layout to perform a layout transpose. For the results sitting at the top left position in the new layout, we could configure BERT to reduce all data into 1 and then send the results directly into the first column and specify the address as the first row. For results targeting at a different column, Feather will reconfigure BERT to reorder the results to column 1. This is achieved through arbitrary reordering. For the results targeting at different row, Feather achieve this by further specifying a different address. Both arbitrary reordering and different addressing enable Feather to achieve column-wise reordering and row-wise reordering, and both added up give Feather the full layout flexibility. Nest and BERT enable Feather to code-switch data flow and layout for each layer, but we haven't decided which data flow layout pair to switch into. To tackle this challenge, we augment time loop with layout evaluation capability and call it as layout loop. Let's first take an overview of layout loop. Layout loop takes the metadata of both workload and architecture specifications as input. These 2 inputs will be used to construct the overall data flow and layout design space. Within the design space, layout loop implements both Explorer to generate new data flow layout candidates and an evaluator to estimate the performance of given pair. Such exploration and evaluation will be carried out in the loop until it finds the optimal data flow layout pair for each layer. Then layout loop dumps the optimal pair together with the performance statistics. Let's now deep dive into how layout loop constructs this design space and evaluates the performance. Layout loop directly inherits data flow or mapping space of time loop. The metadata of workload defines the overall mapping space, while the actual architecture specifications proves the mapping that are not supported by the actual hardware architecture. This gives us the final feasible mapping space. Taking systolic rate as an example, it restricts the order of mapping space to output or with stationary and parallelism space into channel or kernel dimensions. As for layout space, layout loop combines commonly used layout patterns of prior works as unified layout space. Taking the blue input activation as an example, the layout space will include channel last layout that stacks the data from C dimension into a single line. It also includes column measure that stacks data from H dimension into a single line, or a mix of channel and column measure to stack data from both C and H dimension into a single line, or even an arbitrary combination of other dimensions. All of these layouts are supported by some prior work, such as Gemini, Sigma, and Xilinx DPU. Further, we found out that layout with duplication always gives worse performance than non-duplicate version. Therefore, we remove the duplicate layout from the design space. Once finalizing a data flow and layout pair, we could start evaluating the interaction between them. Taking the previous discordant data flow layout pair as an example, the WM parallel data flow requires 16 data from W dimension, but only a single data from H and C dimension. On the layout side, HWC underscore CX2, CX8, WX2, and most provides 4 data from W dimension, such that there is a 4/16 band conflict slowdown. This slowdown extends the latency to 4x longer. To evaluate feather, we construct this framework to take convolution or matrix multiplication from PyTorch, and then call layout loop to call search data flow layout pair for each layer. The optimal data flow layout pair then gets dumped into compilation to generate executable code to run on the realistic GC'24 FPGA. Layout loop could also report the simulated performance statistic. We compare feather with state-of-the-art end-to-end implementation on realistic FPGA using ResNet 50 as workload. Horizontal axis shows layer index. Vertical axis indicates normalized throughput per PE. Feather achieves 2.65, 4.56, and 3.91, higher throughput than Xilinx DPU, Edge TPU, and Gemini separately. This is because of supporting flexible data flows. We also modeled other candidates without end-to-end deployment flow into layout loop for a fair comparison. Feather achieved 2.81, 1.7, and 1.18, 1.36, higher speedup over NVIDIA, Sigma-like, Medusa, and TPU-like. This is because of supporting low-cost on-chip arbitrary reordering. Feather is also a resource-efficient design. A 16x16 feather only uses 44% area of the Sigma at the same sizes, when both being clocked as 1 GHz. This is because 16 input bird could do the same job as 256 input fan. This introducing a square root of n area saving, as shown by reducing the purple bar from middle into a negligible purple bar shown on the right. Feather also simplifies the distribution knob into a point-to-point connection to directly eliminate the area overhead of distribution knob, showing as the red bar in the middle. Both these add up together makes Feather only 6% area higher than corresponding areas like under the same PE sizes. In summary, in this work, we found that data flow layout mismatching could lead to significant band conflict slowdown. To solve this band conflict slowdown, we propose Feather, the first ASIC architecture to enable data flow layout code switching. Functionality-wise, Feather supports arbitrary reordering to ensure zero band conflict. Performance-wise, Feather implements reordering in reduction to hide the latency of reordering behind the critical path. Specifically, layout flexibility is powered by BERT, while the data flow flexibility is powered by nest array. Our evaluation shows Feather delivers higher throughput per PE, runs faster, and being more resource efficient and scalable than the existing design. The Verilog implementation of Feather, full stack layout loop, and FPGA end-to-end deployable codes are all released at the QR code below. We will provide constant support and upgrade. So welcome to drop me an email for questions or potential collaborations. Thank you.